Let's figure out what vision is. Richard of York gave battle in vain. Red, orange, yellow, green, blue, indigo, and violet. Colors. That's what our vision means. Humans are capable of perceiving only a very narrow range of electromagnetic radiation. We cannot see anything after it, much like everything before it. Infrared radiation, as is easy to guess from its name, comes right before the red color. It's also called thermal radiation because we can actually feel it as heat, but are not capable of seeing it. Modern equipment, however, can visualize this radiation. All objects emit heat, or infrared radiation. Electromagnetic waves of a certain wavelength, roughly 0.9 to 14 micrometers. Thermal imagers, or infrared cameras, are capable of detecting this spectrum and translating it into an image that makes sense to us, humans. Dark blue and violet hues, they stand for colder areas. Bright orange and yellow for warmer ones. Contrary to a common misconception, there are no objects in this world that don't emit heat. Even say ice. If we slightly adjust the heat range of the thermal imaging camera, the block of ice will start glowing like burning hot metal. Only objects cooled down to absolute zero, minus 273.15 degrees Celsius, don't emit thermal radiation and cannot be detected by thermal viewers. But achieving this state is next to impossible. What are thermal imagers used for? First of all, to see in the dark, or inside a building filled with smoke, or during outdoor fires. None of these factors interfere with infrared radiation. That's why thermal imaging cameras are extensively used in Army as night vision devices, and in firefighting departments for detecting sources of fire and finding people in smoke-filled rooms. There are also industrial thermal cameras for detecting, say, parts of a residential building with poor heat insulation. Thermal imagers are also used in medicine, for example, to detect areas of inflammation. But there are also some curious things that are seen differently by regular and thermal imaging cameras. For example, this black plastic bag. If I cover myself with it, the regular camera won't see me anymore, but the thermal one will. Actually, it registers my infrared radiation, which passes through the bag. And that's not all. We can reverse the situation. A sheet of absolutely transparent glass, for example, becomes absolutely untransparent for the thermal imager. It simply reflects all infrared radiation, and the entire filming crew can see themselves in it like in a mirror. Although, like I said, it's just a regular glass. If we put two glasses of water next to each other, one hot and one cold, a human eye will most likely not be able to distinguish between the two, but a thermal imager sees it right away. Blue color corresponds to cold water, bright yellow and orange to hot. And by the way, it's all in all a spectacular sight when you place together something cold and something hot. That's how cold water looks, like crude oil. And this is what happens when boiling water is being poured into it. You can clearly see all the mixing layers of liquids with different temperatures. Put your hands on a tabletop and then remove them. You won't see anything, but a thermal imager will detect the heated area of the table in the shape of a hand. The same thing happens if you put a face on the tabletop, like a face of the director of our show. The shape won't be so distinct, but still there would be a mark left, and only a thermal imager can pick it up before it goes away in a couple of minutes. And this is something I wanted to do for a real long time, throwing a glass of water in the face of the aforementioned director. For a purely scientific reason, of course. This is just normal water, but since it is colder than the human body, it looks like ink or crude oil on the thermal imager screen. The face seems dirty, although it is not the case. Yes, hiding behind the limits of the visible spectrum designated for us is a whole other world, as colorful and unusual as the one we are used to seeing. Coming up next, visualizing sound waves with the help of a metal plate and some sand, and electricity and fingerprints with the help of ultraviolet light. Also, the inner side of things as shown by X-rays. All of this on experiments in several seconds. How can you see sound? For example, using equalizer in your music system. Is it possible to spot the effects of the sound? Yes, there are several ways to do that, and one of them, a very unusual one, is about to be shown to us in the Institute of Mechanics. It's called Chladny figures. The first experiments exploring how powder or sand moves on a vibrating membrane date back to the late 18th century. German physicist Ernst Chladny sprinkled some sand onto a horizontally supported metal plate and ran a violin bow along its edge. The sand assembled into a certain pattern. One more bow movement, one more figure. Today, we won't need the bow. The setup is a little bit different, but we'll see the result nonetheless. This is the structure of our membrane. It's basically a smooth metal sheet, rigidly fixed along its perimeter with regular loudspeakers sitting underneath. The speakers are not connected to the sheet in any way, so it's only exposed to air vibrations coming from the speakers. To see the effect, we'll put something fine-grained on top of the sheet. Sand suits our needs quite well. The speakers installed underneath the black metal plate are turned on. The frequency can be adjusted manually in the range from 10 to 150 hertz. And the sand on the plate start forming a pattern. When a metal plate is exposed to a certain frequency, it reaches resonance. Imagine a pendulum which you can swing. If at a certain point you push it or just give it a little nudge, the pendulum's amplitude will increase. It's like a swing set, like when we were kids, we used to go on the swings. Yes, you just have to push at the right moment. The same thing happens to our plate membrane. Sound waves start pushing it with a particular frequency, like a pendulum or a swing set. Resonance occurs, and the vibrating plate tosses the sand up at some places higher than in the others. It becomes clearer from a lateral point of view, and in some areas, the plate doesn't move at all. That's where most of the sand grains are collected. The stronger the plate oscillates, the higher the sand jumps. And since oscillations force the plate to bend, sometimes sand is thrown in all directions, and sometimes the plate goes down. So in the areas of maximum amplitude, which are called anti-nodes, the sand starts moving away. So basically in areas where the plate is bulging, where it's bulging and sagging, the sine wave oscillates both up and down. And those areas where the plate remains almost stationary are called nodes. That's where the sand is piling up, because there's no movement of the plate. Sand can be substituted with any other free-flowing granular material like sugar, salt, colored talcum powder, or ground grain, as long as its particles are small and non-sticky. Also, the acoustic signal has to be of a particular frequency, which is impossible to predict beforehand. It all depends, as they say. Every plate vibrates in its own way with its own frequencies. That's why the resulting Chladny figures are unique, much like our fingerprints. Is the number of these potential patterns finite? It's infinite. I guess the upper limit is determined by the power of radiation, by the strength with which you are pushing at the plate. And also, when frequencies are extremely high, you have your energy dissipating. That is, vibrations are transforming into heat. Is it possible to assemble such an apparatus at home? I would imagine it is. If you have an amplifier, a computer, a thing you want to be oscillating and some sand. So it's very handmade, so to speak. Very doable, yes. Coming up next, X-ray imaging. How does it work? And how do familiar things look inside? Also, ultraviolet radiation. What unusual view of the world will it show us? We have already seen, literally, sound waves during the experiment with Chladni figures and the workings of an infrared camera. Waiting for us is yet another spectrum of electromagnetic radiation hidden from the human eye: ultraviolet. Ultraviolet means beyond violet, electromagnetic radiation that occupies the spectral band between visible and X-ray radiation. Ultraviolet wavelength falls in the interval of 10 to 400 nanometers. A human eye is not capable of seeing ultraviolet, but there are cameras which, similar to thermal imagers, visualize ultraviolet radiation and fluorescent mixtures which start glowing when exposed to ultraviolet waves. Fluorescent mixtures are often used to make special marks in documents, banknotes, and bonds. It's very neat. Under normal conditions, nothing's there. But when you put the object under a black light, that's how a source of long wavelength ultraviolet radiation is called, and voila. This is, for example, how a passport looks. And this is a driver's license. Seriously, who would have thought it looks like this under UV rays? These are, again, special marks. They glow with visible light, but only in the presence of invisible ultraviolet light. X-ray radiation. Electromagnetic waves in the range between ultraviolet and gamma radiation. Wavelength 10 to the minus 12 to 10 to the minus 8 meters. One of the most prominent properties of X-rays is their ability to pass through objects. The denser the material, the more radiation it absorbs. If, for example, you would put your hand on a photographic film and expose it to an X-ray machine from above, you will get an imprint of the hand's internal structure. That's because the radiation will get partly absorbed by the bones, making these areas turn out lighter on the film. At the same time, radiation won't meet as much resistance in muscles and skin, so these areas will turn out darker. X-ray machines make use of the same principle for scanning luggage. Every apparatus contains something like a lamp, which emits X-rays of certain strength and a sort of film, a narrow band of a special sensitive material on the opposite wall of the scanner. Since the material receiving X-ray radiation is narrow, it's not cost-effective to make it the size of, say, a suitcase. That's why the luggage has to move. When passing through the machine, every centimeter gets X-rayed. The images are then summed up, put together like a puzzle, and shown on a computer screen. Darker areas correspond to bigger density of the objects inside, like the ones made of metal. Lighter areas, less compact objects, like clothes and organic matter. Is it possible to fool an X-ray machine, an X-ray scanner? The thing is that when objects are positioned in a certain way relative to each other, these objects might overlap. And in this situation, inexperienced operators basically can make a mistake analyzing the image and, for example, miss some dangerous goods. But first of all, there's an option of re-examining the object, like when you position it in a different way. And second of all, operators need to be more attentive and more experienced. X-ray scanner for passengers is not much different from the luggage one. Instead of the conveyor belt moving inside, the machine itself rotates around the person, scanning every centimeter of his body. Here's my image. Some coins in my pocket, a phone. The watch on my left hand clearly stands out. But if you hide something metal or generally denser than the human body and clothes, then all of this will show up on the X-ray image, even the things I managed to stuff into my shoes. Please follow me for a pat-down. Talking about this X-ray machine, is it dangerous? It depends on the dose. It's well known that even drugs or food in certain amounts are good for you and in certain amounts are bad. Naturally, for screening people, same as in medicine, and for scanning luggage items, we aim to implement a small dose approach. That is, doses we use here are very small. They are comparable to background radiation. A full-body scanner, for example, exposes a person to the amount of radiation that he would receive by staying 2.5 hours on the latitude of Moscow. So the dose is quite small. Let's play a game now. Inside of these black trash bags are various objects. We are going to put them in the scanner one by one and then show you the resulting X-ray images. Try to guess what's inside. Off we go then. And it's on, the first bag. What have we got here? Well, the uniform color and shape leaves no room for doubt. Vegetables and fruits and other foods. This one is more or less obvious. It contains fruit. Bananas, melons, apples, and a pomelo. Here. Altogether, they have roughly the same density, which makes them look almost the same way on the X-ray image. Shall we continue? And what do we have next? It's weird. Some packages, but the density of their contents is clearly different. Here we have sugar and salt. Apart from one thing being organic and the other one mineral, they also have different density and different mass. That's why salt shows up as blue and sugar is brown, as any other organic matter. The next batch. And here we'll finally answer the question of why all liquids get confiscated before the scanning. Even water. Here, one of the bottles contains gasoline instead of water. Try to find it on the X-ray machine. Gasoline with alcohol. It's this bottle. If I didn't know which side it's on, I wouldn't be able to tell. They all look quite similar, especially when the level everywhere is almost the same. Water, acetone, gasoline, a lot of liquids, including the ones which are potentially dangerous, look absolutely identical on the X-ray image. It led to a decision to simply take away all the water. Thankfully, everybody knows about that now, and incidents don't happen so often. Let's move on. Children toys, a blaster, and a radio-controlled car. This is quite clearly an old TV with cathode ray tubes. Again, easy to guess from the shape. Musical instruments, a boombox, a tennis racket, and a ukulele. Another obvious one, a fire extinguisher. A metal cone. You can see how its color changes to reflect its thickness. First green in the pointy part, and then blue. But these are separate objects. What about when there are a lot of them tightly packed into a suitcase? Skills here are essential, as is swift response. The work of a scanner operator has every reason to be regarded as hard. Of course, operators get tired, and normally for every machine like this, there would be a group of operators who change each other every 90 minutes or 2 hours, depending on how their shifts are organized. They have a rest and then pick up the shift again. I had experience in this, and I can say that this factor is indeed present. In 3 hours, I was so tired that I couldn't recognize anything anymore. People can receive information through 5 main sensory organs: the skin for tactile perception, nose for smell, tongue for taste, ears for hearing, and eyes for vision. But even in one of them, vision, we are confined within a narrow band of a huge range of electromagnetic radiation. Pushing these boundaries is, in a certain sense, a goal of all of humanity.
This vibration of air over a heated surface or a barely perceptible trace from the flame of a candle on a wall is called a shadow method. Light passing through inhomogeneous layers of heated air is refracted in them, and as a result, we see an image, a light shadow. In the 19th century, this method was improved. The French physicist Léon Foucault, in the middle of the 19th century, designed an apparatus for controlling the accuracy of manufacturing lenses and mirrors. He put an opaque screen with a sharp edge in the focus of the mirror. It would then be called Foucault knife edge test. The image was focused at the very tip of the knife, and if there were defects on the surface of the mirror, the light reflected from them was deflected and passed by the edge of the knife, leaving a dark spot on the screen. Later, this method was improved by the German physicist August Doppler, and as a result, a new device was invented, which had this rare ability to make video of the air. Here is the device. It is able to distinguish not only inhomogeneous air densities, but different densities in general. Water, gases, and the resulting photos and videos are called Schlieren method. But from the point of view of the modern world, is it possible to say that the device is still quite used? Until now, it's a fairly useful device, and here's why. It allows you to see the real phenomenon around the model during the experiment. You can use computational methods to calculate the characteristics of a model. But until you send the model to fly, or don't make an experiment with it, you don't see how it is blown by the flow of air. You cannot confidently say that the computational methods give the right solutions for this model. Usually, the Schlieren method is used to test purely scientific things. For example, the aerodynamic properties of an aircraft. It's a great way to see the airflow around the model airplane in detail. But we decided to use this device to look at everyday household things. And that's what we got. Here's what the simple action of striking a match against a matchbox looks like. You can see the flame too, but the main thing is the air heated by this flame. With the naked eye, you cannot see it. A glass filled with dry ice, the chilled air, is clearly visible, flows down along the sides. Cotton wool on the stand, drenched with acetone. We see how it gradually evaporates and also flows down. A very unusual shot, a balloon pierced with a needle. The escaping air instantly mixes with the air outside in some incredible mess. A normal shot would show, well, just an instantly bursting balloon, without all this air disturbance. Since the soda contains carbon dioxide, you hardly open a bottle that it rushes down. Because CO2 is heavier than air, it's only with the help of the Schlieren method that we can see this clearly. An electric bulb heats the surrounding air. propane gas from a lighter, and the same gas when it catches fire from a spark. Since the Schlieren method can be used to see different densities of transparent gases or liquids, we can now see what the water looks like when there's an immersion heater put into it. Heated layers of liquid are immediately visualized. And this is glass. It is done roughly, and although it is invisible to the unaided eye, glass is glass. The Schlieren method immediately sees its different densities. It doesn't even seem transparent at all. And finally, this is what the explosion of a firecracker looks like: a burning Bickford safety fuse. And an ordinary hairdryer. After all, the Schlieren method really gives a unique opportunity to make the invisible visible and to look at familiar things from a new and unexpected angle. It's an ordinary morning, an ordinary girl. Here she's waking up. She's throwing back the blanket, getting up. And that's what it looks like when shot with an infrared camera. On the bed, there is literally a trace from the human body. This is the heat that warmed the mattress and blanket, and it continues to radiate from the surface for some time. Just like footprints. You see thermal footprints, not anything else. The shower. With our eyes, we see this. An infrared camera sees a slightly different picture. Streams of hot water leave thermal traces on the girl's body and on the walls. And if you change the temperature of the water, making it cold, it'll begin to resemble ink or petroleum on the screen of an infrared camera. Though actually it is only transparent water, and it is impossible to determine whether it is cold or hot with a naked eye. Wet hair is cold, therefore the infrared camera shows it blue too. A hairdryer gradually dries the hair and, most importantly, heats it. Hair from blue changes to the color red. Usual ice cream, nothing special. But the infrared camera gives a completely crazy picture. The ice cream, which is cold in comparison to the body, is darker than blue. Moreover, teeth, lips, mouth cooled by this ice cream will become the same blue. A kettle which is gradually boiling. The eye would never see the temperature distribution of heat. The infrared camera can do it no problem. You've never seen an electric kettle like this before. Well, that's it. The girls got ready to go and left for somewhere. And we're moving on. What do ordinary objects look like under a microscope? And what is electrochromic glass? See in the next part of the episode. Microscopes. There are several types of them, with each being different from another in operation principle and possibilities. The microscope, from the Greek small and I see, that is, it is a device for magnifying an image or a detail of an image that is distinguishable poorly or completely indistinguishable for the human eye. The simplest example of a microscope is an ordinary magnifying glass, and with the help of the same lenses, the world's oldest optical microscope operates. In general, there are several types of microscopes. In addition to optical ones, there is also an electronic one, scanning probe one, and an X-ray microscope. But we will look at the image received with the electron microscope. Why did all mankind want to look? To get somewhere so that it was closer, 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 so that to see separate elements in more detail, There are two main tasks. The first is related to the quality control of manufacturing detail of structures that mankind produces. What I mean is to complete a production task, to solve engineering problems. And the second task is a scientific one, curiosity. But what is going on there, all the smaller scales? Let's play a little game. I show you the image obtained with the electron microscope, and you guess what's in front of you. Ready? Go! So, what are you looking at? What is it? Paper? Tree? Cellophane film? The correct answer is ordinary office paper, format A4. If you look closely, you can see the cells in one place. These are cells of a tree. Probably in this place, there's a tiny wooden particle left in the paper. Next, what is it in your opinion? A sponge for washing dishes, maybe cloth. In fact, it is butterfly wing scales. They are such porous traps for light. Surprisingly, it is because of them that the butterfly's wing has different colors. How does this happen? Perhaps I'll talk about this separately in another episode. Next object. Here you'll never guess. This is not a fishing net, but stockings for women. An ordinary thing looking so interesting under a microscope. And this? I'll give you a clue. You use this item every day. You can guess. It's a toothbrush. Even under a microscope, it is difficult not to recognize it. Probably just like this. Again, I'll give you a clue. This has to do with clothes. So, this is a Velcro fastener, invented in the middle of the last century in Switzerland, and actually replicating the plant burdock. And finally, the last shot for today. Also, a household, if not ordinary thing. Everyone has it in their house. Haven't guessed? They're particles of pepper and salt together. The round ones are pepper, and the cubes are salt. To see everything. Isn't this the motto of science? And also to understand everything. Understand the essence of things and phenomena. The world around us is an endless puzzle which is impossible to solve with the help of only 5 senses given to us by nature. And people do not get tired of coming up with new devices and ways to look where only new mysteries appear.